So this video is going to go over the periodic table. So far, just a couple reminder, we've been talking about the atom, and what do we know? We know atoms are made of three subatomic particles, protons, neutrons, and electrons. We know the atom is almost entirely empty space. The size is due to the number of electrons outside the nucleus, and within the nucleus, which has all of the mass, contains the protons and the neutrons. We also know that atoms are defined by the number of protons in the nucleus, but there's different isotopes which have the same number of protons but have differing number of neutrons. The mass of atoms, which is on the periodic table, as we've seen and we'll discuss, is really the average atomic mass of all of the naturally occurring isotopes of an element. And at this point, we have some remaining questions. Where did this periodic table come from? And where are the electrons associated with an atom, and how are they influencing reactivity? And so we'll talk a little bit about this first question, and it'll take us a little bit longer to answer those second and third questions. So first of all, where did this periodic table come from? And it really is born of the work of two chemists or physicists, Dmitry Mendeleev and Lothar Meyer. And both of these scientists at the time started to look at different elements, and they started to organize the elements, grouping them together. And Mendeleev started to organize the elements based on chemical properties, so things that react the same, he would put together. And Lothar Meyer started to organize them by physical properties, so things with similar boiling points or freezing points, what's a liquid, what's a solid, things like that. And what they started to do was they started to use this idea of periodicity, which is this idea of there's repeating patterns of properties in elements. And they use this to sort of construct the periodic table. And we'll talk a little bit more about how they did this, and in particular Mendeleev. And if you search the periodic table, there's actually a lot of different versions of the periodic table. And here is an early version of Mendeleev's periodic table. And even at the time, so this is 1871, there's a lot of people working on this, and there's a lot of different ways to organize the elements. So why was it that we end up accepting Mendeleev's periodic table, which is pretty much the same periodic table we look at today? And the answer to that really has to be is Mendeleev is the first person who you can start to see his periodic table here, and as he's organizing, one of the really cool things he does is he leaves gaps. So if you look at this, we have elements going across. So if you look closely, it's copper and then zinc, and then it's gap, gap, arsenic. So what Mendeleev is doing is saying, I understand the properties of these elements. I understand the properties of these elements. There should be elements here. And just because he can't find them or see them, he predicts there should be an element, and it should have these properties. And that set off other scientists to go in search of these missing elements. And lo and behold, they find them. And more than that, they have the properties that Mendeleev predicts. So it's this predictive power, which is really why we have the periodic table we have. The ability to organize it in a way so we can understand how things are going to react. So let's look at our current version of the periodic table. So here it is. This is a periodic table you can download. There's a link to it on our course outline. There's also an editable version if you prefer. So here's the periodic table. We've looked at it a little bit in class already. A couple key points. There's atomic numbers of all the elements. There's an elemental symbol of all the elements, the name, the molar mass of each element. And you can start to see on top of each column are some numbers, so 1 through 18. And so we're going to start to talk more about what this is and why this is organized. So here's another version of the periodic table that's colored, taking out all the elemental symbols. And a couple of things to note is when we refer to periods, so a period on the periodic table is a row moving from left to right. So we have different periods on the periodic table. We also have groups. So groups are the different columns. So what I've color coded in light blue, green, go to the other side, pink, orange, and blue, going down a column. Those are groups. And the really important thing to know is elements within the same group have similar properties. So elements that are in the same column will react in a similar fashion. Now these groups often have names. So taken from your textbook, you can see group 1 is known as the alkali metals. Group 2 is the alkaline earth metals. I'm going to jump to the other side. Group 18 is the noble gases. 17 is the halogens. And those are the 4 group names you should know. So those 4 group names you should know. In the middle, we also have the transition metals, this big block in the middle. And there's also this subset, which is the lanthanides and actinides. Okay, so this is a picture of our periodic table. Now, let's look a little bit more about the data that Mendeleev was looking at and how he was able to organize this. So what I'm showing here is a plot. And whenever you look at a plot, the first 2 things you should always look at is your axes labels. Otherwise, we can't read the plot. And we can see on the y-axis, we have volume per mole. So atomic size, how big is an atom? And then on the x-axis, we have relative atomic mass, right? So what is the mass of the atom versus what is the volume of the atom? And what Mendeleev started to do was he started to generate this plot. So basically, we're going in order of more or less the elemental atomic number of an atom, going across a row, right, and plotting them versus their size. And if you look at this plot, we can start to ask some questions and say, how does the size of an atom change as we move across a period or down a group? So as we go across a period, so each one of these red dots represents an atom. And so if we back up for a second, we can see, so here's lithium, for example, and then sodium and potassium. So if I back up to a periodic table, lithium, sodium, potassium, so those dots that are labeled are going down a group. Those other dots, so lithium, beryllium, boron, carbon, nitrogen. If we come out to our table again, lithium, boron, beryllium, carbon, nitrogen. What's happening as we go left to right across the periodic table, size decreases. We get smaller as we go across the periodic table, and we don't get bigger again until boom, we go down the group. So lithium to sodium gets bigger, to potassium gets bigger, to rubidium gets bigger. So this is all down our group of alkali metals. So we're starting to see, how does size change? We can see these periodic patterns, right? These periodic patterns. You get smaller as you go left to right, and then you get bigger as you go down the group. And you get smaller as you go left to right, and you get bigger as you go down the group. Smaller as you go left to right, bigger as you go down the group. These are the repeating patterns. And again, the power of the table is being able to predict. So if you start to look at patterns like this, you can start to answer, where should we put radium on our plot? And so how would we answer this? Where should radium be? Well, let's go back up to our plot. So where is radium? There it is, right here in group 2, at the very bottom of the alkali metals, right? So it should follow a trend of the alkaline metals, the group 2 of the periodic table. So if we can find the other ones on this plot, so we see, go to the second dot down after the big one, so here to here to here to here to here, and then boom, if we follow this trend line, we should predict this is where radium should be. And indeed, if you actually look it up, we could look at the atomic mass, we could get the volume. This turns out to be a pretty accurate estimate of where radium would be. All right, so let's summarize a little bit that we talked about. So the modern version of the periodic table was accepted because it allowed for the accurate prediction of the existence of properties of unknown elements. The periodic table is organized by groups, which go down a column, and periods, which are the rows going across the table. Elements in a group react in a similar fashion. So that's a really big, important consideration to keep in mind. And there are numerous periodic trends that helped organize the table, The one we've looked at so far is atomic size. Atomic size decreases as we go left to right across a row or a period, and it increases going down a group. Thank you.